Welcome back to the AutoML seminar. Today we have a talk by Caroline Benjamins about carps, a framework of comparing n hyperparameter optimizers on m benchmarks. And please take it away.
Hi, welcome everyone. Thanks. I'm very happy to be invited to this AutoML seminar series. And yes, I have the pleasure of talking a lot about carps. So I'm Caroline Benjamins. I am a PhD student with Professor Marius Lindauer. I'm standing here in Hannover, but this was joint work with many labs from Freiburg, from St. Andrews, from Sorbonne, and from Munich and from Tübingen. So big project. It turned out way bigger than expected. So as a background, carps started as a benchmarking framework for SMAC because I'm heavily involved in SMAC development as I'm the dev lead. At one point, we noticed, hey, if we want to implement new features, we need to benchmark them. And then we saw the potential in developing a proper benchmarking framework. And this is why we have carps now. So let's quickly look at the outline because it's a longer talk. I will give you a quick overview and then briefly introduce background, so the notation and the optimization setting, and show how carps concepts translates into the code. And then I will show you the optimizers and tasks which are included. Then we go to the sub-selection because we have a lot of tasks. And finally, we go to the experiments on the subsets, the analysis pipeline. We will cover some limitations, future work, and then end with a brief summary. So let's start lightly. If you have ever developed an optimizer or an hyperparameter optimization method, you would have found out that this needs benchmarking because we need to assess the performance. And there are some challenges for it because first of all, we need to select appropriate benchmark tasks because we have many at our hand. And we also need to select proper baselines. And we need to integrate those benchmarks and those baselines in an experimental setup. And sometimes also what I did earlier, this benchmarking setup was set up from scratch for each project. And we want to combat this with carps. So carps is a framework for benchmarking. It's a comprehensive experimentation pipeline where we can easily define and run experiments. We have logging capabilities and analysis methods. And carps is a lightweight and unified interface that glues together the optimizer and the benchmark. And it provides easy access to many, many tasks. So we've counted 3,336 HPO tasks from 5 benchmark collections, and we have 26 variants of 9 optimizer suites. And because we have so many tasks, we also proposed disjoint benchmark subsets for development and testing for the task types black box, multi-fidelity, multi-objective, and multi-objective, multi-fidelity, also in short, MOMF. And we also have experimental results available for all baseline methods on those sub-selections. So starting with the optimization setting, suppose we have an objective function. In this case, it's the bebop function number 7. The objective function f is a mapping from the input space x to the output space. And this definition is highly general, so we can cover many task types, and also the objective function can be stochastic. So this formulation allows basically every objective function. And then our optimization setting is that we want to find the incumbent, which is the best performing hyperparameter configuration that minimizes the objective function. And let's inspect the input space a bit more. So what actually is the input space? In the most common setting, it's just the configuration space, and it's what we actually aim to optimize, the hyperparameters. The hyperparameters can be floats, integers, ordinals, which are ordered discrete elements, or categoricals, which are unordered discrete elements. And the configuration space can also contain constraints, conditions, and hierarchies. But that's not it, because sometimes we can also peek into our objective function, and we have the notion of fidelity space. And the fidelity describes where the resolution is. And you can, for example, if you have a neural network training, and normally you train for 20 epochs, that's your full fidelity, that's your full optimization budget in this case, or like a training budget, not optimization budget. And if a lower fidelity would, for example, stopping the training at 5 epochs. And this principle is used in multi-fidelity optimization, where we assume that lower fidelities, so for example, the performance at 5 epochs, correlates with the high fidelity or the full fidelity of 20 epochs in this case. So the configuration space, the input space can consist of the configuration space and the fidelity space, and also of an instance space when we go to the setting of algorithm configuration. Another example would be if we would optimize the hyperparameters of a neural network training algorithm, and we don't want the neural network only to perform well on one data set, but on several. We have then instances, and then we have the instance space we also need to consider, and which also is an input to the objective function we want to optimize. But the important thing is here, we don't optimize the fidelities or the instances, we just optimize in the configuration space. And then we can just define the task with now that we have defined the objective function, because we distinguish between task and objective function. So the objective function has the input and output space, but the task is defined by a specific instantiation of the objective function and together with optimization resources. Optimization resources could be number of function evaluations we have at hand for the optimization, or also the wall clock time available. And also, depending how we define the input spaces and output spaces, we can create potentially many tasks for one objective function. An example would be if we would have multiple outputs or multiple objectives, and we would choose to just optimize one. So same objective function, but we restrict the output space. So in the end, we can have several tasks. And because we can have, depending on how we set up input and output space, we have several common task types. And the most common one is the black box task, where the input space is just the configuration space and we have just one objective. Taking the fidelity space into account, we have the multi-fidelity task type, still one objective, but now we have configuration space and fidelity spaces input. For multi-objective, same principle, we just have the configuration space, but multiple objective. And for month, we have fidelities and multiple objectives. And of course, for each task type, you can add instances, and then you can directly make it an algorithm configuration problem. Now, having defined the tasks and the objective function, let's check out sequential optimization. How do we actually optimize? And I'm showing you the definition after Garnett's book. And sequential optimization mostly starts with an initial data set of observations, which can also be empty. And then we have a certain policy, and based on the policy, so the policy takes the evaluated data set into account and proposes then the next point to query. We observe this function evaluation, and then our data set is updated. And also we have a method to determine the best performing incumbent configuration, which is quite easy for single objective because we can just compare the objectives, the objective values. It becomes more difficult for non-deterministic objective functions and more for multi-objective, and also even more if we add instances into account. So this is repeated until we reach a termination criterion. And in this sequential optimization scheme, we can directly map the concept of ask and tell, which you will meet with a lot of optimizers. So when we talk about we ask the optimizer something, the optimizer is asked to return a configuration or a point, next point to query. And when we tell the optimizer the new observation, it updates the data set and it might also update its policy how to select the next point. And this updating of the policy can also technically happen in ask. That does not quite matter, but the important point is that we have this distinction of ask and tell, and then the function evaluation is decoupled from the optimizer itself. And this is also directly translated into carps, because now I'm showing you the interface, which glues the optimizers and benchmarks together. On the one side, we have the optimizer with ask and tell embedded into a run method. And then we have the task defined with the optimization resources. And then we have this loop where we ask for a point, objective function gets evaluated, and the observation goes back into tail, and the optimizer can adapt its policy. And also, this concept is directly mirrored into the code, because when we define the optimizer, it's literally inheriting from this parent optimizer, which controls the optimization flow. So when ask and tell is called, so for an actual optimizer, we just need to implement ask and tell. Same goes for the task. The task is directly defined as you saw in the visualization. It has the objective function, input, output space, and optimization resources. And also those subspaces are directly defined as before. So we have the configuration space, fidelity space, and instance space. And before we go to the subselection, we look a bit more how carps technically works. So we have many optimizers in even more tasks, and we configure those with configuration files via Hydra. Those are YAML files which fully determine the behavior of the optimizer or fully determine the task. So for example, we could create several dep configurations with different mutation factors. And this way we can keep a very good track of what are we comparing with what. Same goes for the tasks. Here we have a YAPO task. I don't show the complete example because the config space is quite long, but the task is fully defined together with the objective optimization resources. And also a nice other benefit of Hydra is that we can easily parallelize the runs on Slurm or other clusters with a simple run command. So in this case, we run carps on a local cluster. In this case, you could also do Slurm or anything else which Hydra supports. We select the random search optimizer, and we want to optimize or run each black box subselection development task. This is nice because we can do some glob operator. And then we want to run for 20 seeds, and we define the output directory, and this directly creates the grid of experiments. And if it runs, it looks like that during running. And yeah, if you haven't heard of Hydra, I would highly recommend to check it out. It's not only useful in this context, but it makes the overview much, much easier of experiments. And also since I'm using Hydra, my life became better. So I highly recommend also Hydra. Last but not least, we can log to files or the database. File logging is in a format which is human readable. The database, of course, also, but you need a database for that. In this case, it's an SQL database with exactly the same information. So for example, we save all benchmarking. We save the complete benchmarking setup, so seed, task, and actually we also save the complete config, so the experiments can be restored, and we can really see which parameters we used. And we can also control experiments with Hyperparameter so that everything is controlled via database. So much about the technical stuff. Let's check out what carps includes. It includes many optimizers from different frameworks. We have Axe, deb, Hibo, Nevergrad, Optuna, of course, random search, scikit optimized Mach3 and SignTune, and in total 26 variants. And we set up the configuration files or the configuration for each optimizer or sub-optimizer to use the default settings. So we didn't play with the defaults in this case. And then on the other side, we also have many HPO tasks from HPO bench, YAPO, Bebop, Pymo, MFP bench. And you can see a bit how they are distributed across the different task types. So we have many black box and multi-fidelity tasks, not so many multi-objective and month tasks. And we have some low to moderate high dimensions. And in fact, you could also with Bebop create artificially high dimensions if you would want to do that. And as objective functions, we have some real objective functions, which in the HPO bench case would be training an ML regressor, for example. But we also have many synthetic functions, so this also counts to real objective functions. And we also have tabular benchmarks and surrogate benchmarks, with the most coming from YAPO. And we also have some nice distribution of floats, like of the hyperparameter types. So you see, those are a lot of tasks, and also just for Bebop, those are 1,317. And when we develop an optimizer, we might not want to benchmark on all of them. First of all, because those are many tasks, but also we can assume that those tasks are not equally distributed and actually can introduce some bias. So this table is from Seniki et al., where they demonstrated what happens when you run the same optimizers on different benchmarking suites, which actually are quite similar, but then the devil is in the details. So for example, what you can see here, this is differential evolution. This is real space particle swarm optimization. This is CMAES. Those are the different benchmarking suites. And this is a 0 indicates whether we have a statistically significant difference, and 1 does not. So depending on which benchmark, so first of all, we see that those results for Bebop, CC, several CECs, they are not the same for each benchmark. So we see different numbers for each case. And also, if we want to highlight, for example, differential evolution as a great method, we could, for example, pick this benchmark. So depending on how you set up the benchmark, the results, you can create different results, which is, yeah, of course, yeah, we need to define the task before and not pick the benchmark after to show our method is best. So the solution here is to subselect in a way that we don't have a bias in it. And the intuition is that we want to subselect tasks that cover the space well in the performance space. So how do we get to this idea? So first of all, we formulate the subselection as an optimization problem. And for this, we need to represent the tasks in a feature space. And then if we have this feature space, we can select k tasks, or in this case then points, that best cover the space spanned by the complete tasks or points. The question now is how to represent the tasks. And it has been shown that features for HPO and black box tasks do not capture the objective function well enough for AutoML approaches. Therefore, we resort to subselect in the performance space spanned by the final performance, like the incumbent cost of different optimizers, because this reflects the behavior of the optimizers. And in this case, you can see the performance space spanned by for the black box task from random search, SMAC3, and CMAES. And those are 3 optimizers which behave quite differently, and where we expect that they all have their strengths and weaknesses. And so we also expect that we can get a diverse subset. And now, of course, we need to describe the space coverage, and we do that with a star discrepancy. And for this, we formally defined a set of points, or a performance matrix P, which is a set of vectors y. And we have m vectors y for m tasks. And each vector is the final performance normalized. So we can also compare across tasks, or so that we live in the same performance space. And the vector has the length of n optimizers. And in this case, as you just saw, this would be the performance matrix P visualized in 3D. And this is also an example. This is not from the subselection, but a general example in 2D with this point Q, which I will explain the importance in a second. So with this setup, we can now calculate the star discrepancy, and it's defined as the supremum over all possible points Q. And the point Q can live in this unit cube, in this case in the square, because we are in 2 dimensions. In 3 dimensions, some sub-box of this box, and you can scale up as you can imagine. And the important thing is that the square or the cube is always centered in the origin. So it's the point that minimizes this, and this is basically the number of points that fall into this box divided by the total number minus the size of the box, which is the Lebesgue measure. And in this case, we just need to multiply the Q points, the Q coordinates. And in this case, for this example, for example, we have 7 points that fall into this area. We have 60 points in total, and the total volume is 0.16, so we get a star discrepancy of 0.0433. So this way we can measure how well the space is covered, and it's basically saying how much we deviate from a uniform set. And also, like you probably know, Sobol and Halton sequences, those are also low discrepancy sequences. So now we have we need to describe the algorithm. So the goal is find k points that minimize the star discrepancy to the complete set. And there are exact methods available for 2 dimensions and heuristics for higher dimensions, both introduced by Clément and al. And we do the following with restarts. We select a random subset with k points, so randomly k points, and then we greedily swap points to reduce the discrepancy. And you can imagine that depending on how we initially select those points, the results can differ quite enormously. And this is why we do this with restarts. So that's the algorithm, how to select the tasks or to select the points to cover the space quite evenly. And then in summary, no, not the summary yet. This subselection also has hyperparameters, unfortunately. And we have the following desiderata. We want that the def and test subsets should have the same rank for the optimizers, and the performance should be significantly different so that we can actually expect something to see. And the hyperparameters are, of course, the subset size, and also whether to transform the source, log transform the source space. This came from my observation that if we look at this, everything looks quite crammed in this corner, and if we log transform it, we can already cover the space a bit more evenly. And so the complete procedure is we run for different Ks, log transformed or not. Then we calculate the performance ranks of the optimizers now only on the subset based on a non-parametric test, which I will introduce later. And we keep the combinations where the rank remains the same between def and test. And from those, we keep that with significant differences. And from those, finally, we pick the combo which fits the source space best. That means the combination with the lowest star discrepancy. So in summary, we subselect via optimizing the star discrepancy. And for this, we run 3 optimizers with different optimization behavior on all tasks of one task type. And in this case, for the black box task is random search, CMA, ES, and BO. And then we span the performance space with the performance tuple. And finally, we subselect those k points which describe the space best. And we do this twice to create, without replacement, to create a def and a test set. So let's look at the results of the subselection. In this case, I represent the point matrix in a 2D space for visualization reasons and for matplotlib reasons. And you can see quite well that the space is covered by the subselection. And we also have, from each benchmarking type, we have members, and also we have some diverse dimensions. Also, for example, for multi-fidelity, we just have HBO bench and YAPO and probably also MFP bench. But in this case, for this, it hasn't been selected. Okay. So for this, we, for example, reduce the black box set from 1,317 to 20, and for example, the almost 2,000 set for multi-fidelity to 30. So we are ready to look at experiments, or first to define the experiment setup. First of all, we run everything with 20 seats, and we also need to define the optimization resources. And for this, we used the formula of Yapogym for the number of trials, which depends on the dimension. For example, for 2 dimensions, we have 77 trials, and for 3, I think 134. And then also running the benchmark doesn't take that much time. So for all seeds, for one optimizer for black box, we just need 21 hours. So how do optimizers perform? So the first idea is, let's visualize it with a box plot. And here you can see one problem. So in this case, this is just the incumbent cost normalized, but all tasks, all seeds, so really the raw values except for the normalization. And with all the outliers, A, we cannot see anything, and B, we can also assume that the performance distribution is not normal. So let's remove the outliers so we can see a bit more. So here we can see actually that, for example, X has a very nice distribution in this case and definitely performs better than SMAC 3 HPO facade. What I also visualized here is the mean, which is way lower than the median in this case. And the question mean versus median is also important because it can also change how well the optimizers are perceived. And for this case, I think, yeah, also Lennart, you recommended me the AutoRank package. So we answer this question by comparing on rankings, and the rankings are based on a non-parametric test based on the package AutoRank with a significance level of 0.05. And we perform the ranking on the raw performance values of each task. So in this case, they are not normalized because we compare intra-task, and the performances for each task are averaged over seeds. And now we need to decide which test to use. So we just follow this flowchart. So we use the frequentist approach, and we have more than 2 populations because we have more than 2 optimizers. And as we just saw in the box plots, they are definitely not normally distributed. So we resort to the Friedman test with Nemeni post hoc test, which basically compares the median. And our means of analysis and visualization is then the critical difference diagram. So let's check it out. So now I show you results for the black box subselection test set for 20 seeds, and those are 20 tasks. And we get this ranking. This also quite coincides with the box plots. And we can see 2 things. First of all, that we do have a clear ranking. Some of them are also really close to each other. So this x-axis signifies the ranking, and this is the critical difference. And 2 optimizers need to be further apart than this distance to be considered statistically significantly different. And in this case, we see that Ax is still not significantly different with CMAES, for example. And we can only not do this for the final performance. We can also do this over time, so we can see how the rankings behave. And we can also inspect a bit anytime performance. In this case, the number of trials needed to be normalized because we have different dimensions, so a different number of trials. And we can see that the ranking stabilizes like at 70%. And also for the rest of the task types, this is also similarly true. It stabilizes after 60 and 80%. And also in this case, we don't see it, but if there's a gray area, it's the indication that nothing is significantly different yet. But in this case, we can distinguish quite nicely. And of course, we have one downside for ranking, which is we just look at relative performance. And this is why we also have some heat maps where we can inspect each task and each optimizer. And in this case, also the final performances per tasks are averaged over seeds. And then it's plotted with like how well they perform. And we can also see 2 things here. First of all, we can see strips of yellow on like very light strips. So the lower, the better in this case. And we can also see some dark strips, some darker areas here. And that means our subset actually seems to contain easy, medium, and more difficult tasks. So one thing achieved, we want to have quite diverse tasks. And we can also see another thing, that also for certain tasks, some optimizers perform quite well and others do not, and also vice versa. And that can hint to a complementarity of optimizers, actually. So I want to briefly talk about the path to your or my optimizer. And the first question is, you really need to be clear about why you want to develop a new optimizer. And by why, the question is, which problem do we want to solve? And for this, we clearly need to define the task area where to advance. I also remember a conversation I've had with Aaron about this, and where he also said you need to clearly define the tasks and then start building the optimizer. And then you can start developing in this task area. And it's also very beneficial to still verify the general performance with the proposed subset and consider different ways to inspect results, because the performance distributions might or are probably not normally distributed. And maybe we can also see bimodal distributions and look at some failure cases, like why does the optimizer not perform well on certain tasks. And we can also assess how robust the optimizer is to different seeds, for example. And then we need to carefully report for the task area and the general case without generalizing conclusions. And you can use the optimizer template of carps to ease the complete process. Because we also have tutorials for how to define your own tasks and your own optimizer in carps, and it's quite, in my opinion, easy to add, but I'm also developing the framework, so my opinion might be biased. So last but not least, let's talk a bit about limitations. So first of all, the scope is a clear limitation because we only have hyperparameter optimization tasks so far. And here we are very open for collaborations or like for contributions, because it would be great to add more diverse domains, for example, or like more task areas like high-dimensional Bayesian optimization, or some bio-AI protein design tasks, or some mechanical engineering tasks, which differ, which objective functions probably differ a lot from HPO. And another limitation is that with the current config space, we cannot provide generic grammars or generic pipelines, because or for cases like neural architecture search, if we have some special definition, or if we want to build or configure complete AutoML pipelines. So this is also a limitation, but it's only a limitation by a config space, and the actual configuration space can be easily swapped out in carps. And as it's Python, we just move Python objects from A to B, so it's extensible. And also regarding the subselection, there are definitely other space diversity metrics, and also the L star discrepancy has some bias to select points in the upper right corner of the unit cube. But also for this, there are remedies, there are like symmetrized versions one could use. And also for the benchmarking setup, I've showed you the rule we've used to determine the number of trials, but it's just one way. It doesn't cover cases like where we only have very, very few number of objective function evaluations, or where we have a super high budget. But in this case, it's also a matter of configuration files and easily change, but then we would need to think about creating a new subselection again. It depends. So for those, we directly get some future work. And then in general, as I said, we would like to extend the framework to include more optimizers and benchmarks, extend the task types to include constraints and other domains. And also, because we are in modern time with HPC, so with high performance clusters, it would be great to integrate parallel execution system, which is non-trivial, but that would be a great future work. And also active benchmarking, so actively selecting the benchmarking instances until we have a high certainty of the underlying optimizer's performance. So, as in a nutshell, we can make developing optimization methods more easy with carps. It's a framework for benchmarking and optimization methods on M benchmarks. It has a lightweight interface between optimizer and benchmark, which the concept also directly translates into the code. We have many different HPO tasks from different task types like black box, multi-fidelity, MO, and MOMF. And we also have sub-selection for those task types. And also, as I said, tutorials available for easy integration of your own optimizer or tasks. Also a little success story, we also developed Syntactic Bench, which is a carps compatible benchmark to benchmark synthetic algorithm configuration. So you're very welcome to check out the paper on arXiv and to check out GitHub, and we are also welcoming any questions. So thanks a lot for being here with me, and try out carps.